In this next example, we're going to look at a slightly more advanced buffer overflow. So previously, our buffer overflow looks something like this. If this right here was the structure of our stack frame, where we have our local variables, the saved base pointer from the previous calling function, and the return address into the caller along with our function parameters, what we would do is have some sort of a character buffer here that say was length 50. Maybe we would have some other local variables underneath that on the stack, maybe of length 8. We would have this saved base pointer from the calling function, which is going to be another 4 bytes, so there's an example address. Then we would have the return address back into the caller. That would be another 4 bytes, and then there was the sample address. So if we have 50 bytes plus 8 plus 4 plus 4, then we would need 66 bytes, which our exploit string will fill. So we've got 50 A's to fill up the first buffer, and then 8 B's to fill up the local variables, 4 C's to fill up the base pointer for the caller, and lastly another 4 D's to overflow the return address. And so what we would do in our previous example, after injecting that string, we'd replace sort of these values with the values from the string above, where in the instance where we're jumping to some other local function, the D's would actually be replaced by 4 bytes that form the address of some function we want to jump to, right? So we basically trample over all this data in the stack with our long sort of string that was fed in via some unbounded or unbounds checking function, and it would eventually overwrite this. Then as the function started to return and popped all of these variables off the stack, when it went to return to the calling function, it would pop our corrupted value off the stack into the instruction pointer. Okay, but what we're going to do this time is something a little bit different. What if there is no local function that we want to call? What if the code and instructions that we want to execute don't already exist in the program? We can introduce new code as compiled instructions into the program's memory, and rather than jumping to another local function, we can jump to those compiled instructions. So now our exploit string is going to look something like this. We might have some amount of padding at the beginning, which we'll talk about in a second. Then we have our compiled instructions. Then the last part of our exploit string, like we did before with putting an address into the return address, here we're still going to inject an address, but it's actually going to be the address of the first compiled instruction that we're injecting. So we actually want our code, when it returns from this function, to actually jump backwards into code that we've now injected into the stack. So we'll resume program execution here rather than at some other function off in our program. We have to inject some amount of padding because it's likely that the number of our compiled instructions plus the address isn't exactly equal to the length of exploit string that we need. It would be really difficult as well to determine the exact byte that we need to jump to. So quite often, the padding is actually a series of what we might call like garbage instructions, instructions that don't really do anything. There's a really excellent instruction that's well suited to that in assembly. It's called no-op, or no operation. Basically, it's an instruction that literally does nothing, and it's represented by the byte 90. Okay, so the idea is that rather than just having padding, we would replace this with a whole bunch of no-op operations until we've sort of fleshed out or filled up the amount of extra space we have in our buffer. What this allows us to do is be a little bit more vague with the address that we want to jump to. Now we could land at any of these instructions or the first instruction right here, and they would all be valid because, for example, if when the function returns, we landed at this instruction right here. Since no-op is still a valid instruction, it would run that, and then it would run the adjacent no-op, and then the adjacent one, and it would run as many of the no-ops that we have in a row until it eventually lands or slides into the first address of our compiled code. That's why this operation is often called a nop slide or a nop sled, or whatever you want to call it. So that's what we're going to do for our next example. We're going to determine how big the buffer is, along with all the other data sitting on the stack that we need to overflow. Then we're going to compile some of our own code, build that into our exploit string along with a bunch of no-op padding on the left. Then we're going to determine where this data winds up in the stack when we do inject it, and we're going to replace this address with the address of our newly injected code so we can run our exploit that way. So if we're going to execute code that lives inside of our stack, we need to figure out where that code is. Right? We need to figure out the address of that buffer in the stack that we're going to jump to. There are a few ways of doing that. There's also some trial and error. There's some experimenting you can do. But for the sake of just getting through our example, we're going to cheat a little bit and assume that we have the ability to modify the source code of the original program. So we still have our example file, and we're going to make a small change to it. We are going to jump down to the bottom of the getMessage function right here. And we're actually just going to print out the address of that buffer variable. So one of the format specifiers in C that we can use is %p, which basically prints you know, some kind of a variable as sort of in like a pointer format. So it'll put the OX and then the hex address for us. So we're going to print the address of the buffer like that. So now when we run the program the first time, it should spit out the address of basically where that string lives. Okay, I'm going to save that, make. Now if we run example1.out, and it asks us for a string, say hello, and then the address of the buffer is ffffd0be. If we run that again, you should get the same address if you remember to make all of the right changes to your system. If you're getting different addresses, it's because you didn't disable the address space layout randomization, or ASLR. To do that, you need to do sudo syscontrol kernel.randomize va space equals 0. Right? And now every time you run that program, you should get the same address showing up as the address of that buffer. Okay. Now we're going to see if we can actually jump to that address or one nearby. So we're going to run our exploit again. We're going to say Python, and then we're going to print 50 A's. Now we also know that there's about 12 bytes of additional content on the stack, including the old base pointer, other local variables, things like that. Now the address that we want to jump to, so it was be d0ff. Now we're going to pass that into example1.out. Okay. So the address of the buffer didn't change. We crashed. We got our seg fault. So we say gdb analyze the core and then quit right away. Oh, sorry. There. Now we should be able to get our core dump. Okay. Terminated with a seg fault. We landed at ffffd0f0. That's close to where we jumped, d0be, d0f0. It could actually be that we were able to execute an instruction or two before we crashed. Again, we can confirm this just by saying, you know, d0aa. D0ac. So again, we're landing pretty close. There's a number of reasons that might account for having moved by an extra byte or two. Regardless, we know that we're landing in and around the right area, and the padding that we're going to inject into the program with a bunch of no-ops is going to take care of that for us. Okay, so we know that we can inject, or we have the address of our buffer, and then we can kind of jump in and around that area. Okay, so now we need some code to actually inject into our exploit string here, rather than using just A's and B's and the eventual memory address. Okay. So what we're going to do is write a short assembly program that makes a system call, and then we're going to grab the opcodes from that compiled program, and that's what we're going to inject into the program. So that will probably make more sense as we go along. So we're going to call this shellcode.asm. Shellcode is the traditional name for sort of these compiled programs or sequences of opcodes that get injected to programs because typically, I mean, you're spawning a shell, right? So we're going to global start. We have to tell the program where it starts. And by convention, ELF files want to look for a label called _start when we're compiling. We start our text segment, so we're going to insert instructions. Here's the start label for the program. And the system call we're going to write is pretty short. I'm going to write it first and then explain it. So we're going to move into EAX 1 in hex, or 1 in decimal, I guess. Move into EBX 0, and then we're going to call interrupt 80. So the format for this and the format for system calls in 32-bit executables in Linux went something like this. It's changed now, obviously. In 64-bit, we use the syscall keyword instead of calling this interrupt. But first, into EAX, you load the system call number. So every system call has a number attached to it. So for example, exit is system call 1, fork is system call 2, read and write are system calls 3 and 4 respectively. Okay, so if you wanted to call any of those low-level operations, that's the number that you move into AX. There are good references on the internet for finding that. Then in the remaining registers like BX, CX, DX, etc., you put the parameters to that system call. Right, so typically when we would exit a program, we could say something like exit success, where exit success is actually just a macro for the value 0. Right? When a process returns with a value 0, it means it exited successfully. If it returns with anything but a non-zero, we know there was some kind of error code being generated. So this is what our program is doing. It's really simple. It's literally just calling exit, but we can confirm that that code is running. Okay, so I'm going to save this. Then we're going to assemble it. So we're going to use NASM. So -f, we want to create a 32-bit ELF file, and we're going to create that from shellcode.asm. Okay. That should have created shellcode.o for us. Then we're going to compile it into an actual executable so we can run it and make sure it works. So we're going to say load elf i386 because that's the type of executable we want. We're going to compile it from shellcode.o, and the output file is going to be shellcode.out. Okay, no errors, we're good. We have a program now called shellcode.out. If we run file on that, we'll see that it's a 32-bit ELF or executable for Linux. We can run it. Won't do much because it literally just calls exit, and we can confirm that by saying strace. Okay. So there's the first call to exec that actually starts the process, and immediately the exit system call is made with the value 0. Again, to confirm this, maybe we could try putting in a different value to see what it exits with. So if we just want to make sure that our program's actually working properly. So I don't know, let's put the value of 8 as the return code. So we'll assemble that and then link it, and then strace shellcode.out. You see here we exited with the exit code of 8. So we're just going to restore that back to our original value. Now, we need to extract the compiled instructions that we call opcodes from this program. There's a number of ways to do this. Probably one of the easiest is just to say object dump -d on shellcode.out. Okay. So the format for object dump is it shows us the assembly instructions over here, unfortunately in Intel or AT&T syntax, the offsets within the file, and then these are the opcodes, the compiled instructions right here. So these are what we take and we're going to be injecting into the program. So these sequences of bytes. However, there's a bit of a problem with our shellcode, and this is part of the fun of writing shellcode. It can be a little bit of a puzzle. If you recall, in C, the null character is a string terminator. So if we called gets and into some buffer, and into that we fed the values B8, 01, 00, 00, 00, BB, and so on, gets would start reading values into this buffer, but then on the third byte, it's going to hit a null, thinking it's reached the end of the string. So it will only read up to here. It will stop reading. It won't capture all these additional bytes. So when we write our assembly that we eventually link into and compile and link into these opcodes, we need to think of ways to avoid having these nulls in our instructions. So if we re-examine our code a little bit, we'll notice we were actually being a little bit inefficient. Okay, so first one, move EAX the value of 1. Well, I mean, we're moving a single value, a single byte value, into a 32-bit or a 4-byte register. We actually only need to move it into the lowest part of that register, right? We don't need to put something into all 32 bits or all 4 bytes. Again, if we look at the opcodes that we got, see, we're moving 1 into EAX, but since we're addressing EAX as a 4-byte register, we actually have to move in a 4-byte value. So we're moving 0, 0, 0, 1. There is an instruction that will allow us to move just 1. Right? It's move AL 1, like that. That should be just a 2 opcode instruction. We can confirm that. If we go back to our shellcode, if we just move 1 into AL, which is, you know, the single byte, like low half of that EAX register. Okay, so if we go back, we run all of our build instructions again. So you noticed moving from move 1 into EAX to move 1 into AL, we were able to drop off the additional zeros. You'll notice the opcode has changed a little bit because referring to move into EAX is opcode 8B, whereas move into AL is B0, but that's fine. We have 2 separate bytes here. I mean, you might notice that there's 2 consecutive zeros there, but that's not how getString works. It'll read 1 byte at a time, so it won't see these 2 consecutive zeros as a null. Now, the other problem, move 0 into EBX. Okay, even if we just did move 0 into BL, right, we'd still have move and then the 0. So we need to think of another way of getting a 0 in there. The classic way of accomplishing that in assembly is to do something like this. Right. When we XOR a value with itself, because of the nature of the XOR operation, we should get a 0. So what this will do is effectively 0 the BX register. The only other thing that we should do, just to be safe, we moved 1 into the lowest byte of AL, but we didn't know what was in the first 3 bytes of AL. Right, there could already be data in that register, and we don't want to end up calling some bizarre system call like, you know, 3001 or something like that, because there was existing data in that register. So to be safe, we're going to XOR out the EAX register. Okay, then move 1 into it, XOR out the BX register, and then call our interrupt. Let's see what we get if we now build this. Okay, so if we look at the instructions or the opcodes, we got 31C0, B001, 31DB, and CD80. Great. We managed to accomplish the same program without getting any nulls, or the other character you got to watch out for is 0A, which is newline, because sometimes that'll be recognized as a string terminator as well. We can confirm our program still works by running strace on shellcode.out. Again, runs, calls exit, it's fine. So these 8 bytes are the instructions or opcodes or shellcode that we're going to be injecting into our vulnerable program. So we've written our shellcode to call the exit function, and we saw the bytes when we ran object dump-d on our shellcode. Rather, we saw the opcodes. Right? So these 8 bytes are the instructions that are going to call the exit system call for us. So we need to copy those out now and inject them into our exploit string that we were building over in the other tab here. All right, so this one. Unfortunately, it can be a little bit of a pain to try to copy these out, especially if you get longer shellcode than this. You can end up with a couple hundred bytes if you're writing some sort of longer piece of shellcode. So one thing you can do is write like a bit of a one-liner in Bash to just strip out those bytes for you. So something like this, where we're grabbing any lines with hex characters on them, we're grabbing things after the colon, we're grabbing the first two fields, then stripping out tabs and new lines. While not exactly pretty, you could make this more efficient if you wanted to, but that's going to give us the 8 opcodes that we need right there. So we're going to take these and copy them. And we're going to put them just before the return address that we're jumping to. Again, the return address here being the address of the start of the buffer that we're overflowing. And we need to go and hex escape all these bytes to show that they're actually bytes and not ASCII characters. Okay, so we're going to put that right before the return address. Now we need to make some changes to the size of our overflow, right? Before it was 50 bytes to overflow the buffer and another 12 to cover the local variables, the previous base pointer on the stack. So we've just included 8 bytes, so we need to subtract 8 bytes from one of these two values. Okay. So what we'll do is maybe just subtract 8 from here. So we're going to have 50 A's still to fill the original buffer, 4 bytes to cover a bit of stuff that's sitting on the stack. Then our opcodes are going to get put right after that. And then we're going to have our return address. Okay. Now the problem is our return address right now is pointing us to the first letter A that's in the buffer. That's where it's going to jump to. And A is not really a valid instruction and it won't execute. And we don't know the address of the first instruction of the opcodes that we're injecting because it's going to be somewhere down in the buffer. So to make it a little bit easier for ourselves, let's actually, rather than printing A's and B's, let's print just a bunch of no-op instructions. That way, no matter where we jump to, we're going to land on a valid instruction, and we're going to keep executing no-ops until eventually we hit our shellcode. So rather than have 50 A's and 4 B's, I'm just going to print 54 no-op operations. Okay. Now, if we run this, you'll notice we didn't get the message that the program crashed, right? We got in main, calling get message, it did read our message, printed the address of the buffer, and at that point, that function would have exited, or it would have returned to main, where main would have printed a couple messages for us, right? If we look back at our source code file, we saw that after we run get message, it should come back here into main, print back in main, and then print exiting in success. Well, it didn't do that, right? Nor did we get a seg fault when the program crashed. We actually managed to exit cleanly from the program, which meant that our call to the exit system call was successful and it worked. It's not super fancy. I mean, we can't really see much output there. It's not terribly exciting, but we know that we were able to inject code and it worked. The next step would maybe be to modify or write some more exciting shellcode that does something meaningful.